So, last time you guys talked about perceptrons, which is a way of classifying data points into different categories. And we're going to move to logistic regression today, which addresses some of the weaknesses of deterministic perceptrons. And along the way, we'll talk about linear regression, which is kind of an important tool for understanding it, and also just a useful algorithm in its own right. So here's a picture of linear regression, where we have two input variables, x1 and x2, an output variable we're trying to predict, and then this comes up with a best fit surface. But we'll get more into that soon. So, when you were talking in the last class about classification, the problem setup would be you'd have an x and a y, and then you try to predict the y given the x. And the y could take one of a discrete set of possible values. So here it could either be spam or not. Here it could be any of the digits from 1 to 9. And here's, the object we're trying to classify. But to run a perceptron and also to run logistic regression, as we'll see later, what we need to do is we need to turn that object into a vector. And this is called the feature vector. And so that's this first step. And either someone else is doing it or you're doing it, but at this point the machine is not doing it. And then what the machine does, the computer, is this step. So the feature vector might be, how many times does the word free appear, and so on. What's the value of this pixel? Is it on or off? That's what you guys talked about last time. So linear regression is a solution to a different problem. So it's not trying to predict, is this x in this category, that category. For linear regression, you're trying to predict a numerical value. So let's say you have there's some office space, and you're trying to predict what the market rent will be. Or let's say you have two pictures of people, and you're trying to predict how compatible they'd be on a dating app. This is, for those of you who don't recognize it, this is the President of the EU and the Secretary General of the UN. Those were the images I had on hand in my downloads folder of my computer. Okay, and so it's the same kind of deal. You create a feature vector first to use the methods we're going to talk about, linear regression in this case. And that's going to be a vector. So for reasons I'll talk about later, you're going to want the first feature to be a constant. So you can see that's going to take a value of 1 in no matter what the input is, no matter what x is. This is going to be a 1, the first entry of the vector. And then maybe if you're trying to predict market rent, you'd say, okay, well, how many square feet is it? What's the distance to BART? How many offices are in there? How many directions are there views? And you might look at the pixels for these images. You might do high-level features like, is the picture outside? And then you can do linear regression to go to use these feature vectors to predict whatever value you're interested in. Any questions at this point? Yeah.
What is
84,000 is dollars per month. So, yeah, I haven't put the units in here. I mean, this would be unitless. This would be square feet. That would be miles. Well, you've seen weight vectors last time, and you're about to see them again. And so the weights would have units to kind of make it cancel out. So this would, the weight corresponding to this would be, I guess, dollars per month per square foot. But for the sake of the algorithm, we don't need to keep track of the units. They're just numbers to us. But for the meaning of the problem, let's say this is how many dollars per month to rent this office space. Okay, so this is the slide you saw last time. This is for linear classifiers. You have inputs that are feature values. Each feature gets a weight, and then the sum is the activation. This time we're doing linear regression. We're not interested in outputting a binary yes or no. We're just interested in outputting a number. Well, here's a number. Let's output that. That's basically what linear regression is. So instead of it being the activation, this is our answer, basically. And we use this notation sometimes. So this depends on the weight vector W. And then instead of just as before, we take the features, we multiply them by the associated weight, we add them together. But last time, we said that the final thing we did was say, okay, is that number positive or negative? And we just skipped that step. We just output the number. So this is kind of even more basic than the perceptron algorithm from last time. So in those examples from before, let's say these are our weight vectors. This is just the office rent example, actually. So here we have a weight vector, and maybe we'll multiply this constant by 5,000, we'll multiply the square footage by 0.8, and so on. And then if this is our weight vector, then the prediction of linear regression is the sum of these products, which is the dot product of these vectors. And I have a little question for you guys, which is when I was just randomly making up the weight vector here, I made one of them implausible. And can you tell which it is? Remember, the problem is trying to predict how much rent for office space, for a given piece of office space. These are the features that we have for different offices. And then to predict the rent, we're multiplying those features by these numbers, adding them all together. Which one of these has to be wrong? So let's go through how you would get to the number, the predicted rent. So you'd take the constant 1, you'd multiply by 5,000, so you're basically starting at $5,000 per month. Then you add the square footage times 0.8. Then you add the distance to BART times 100. Then you add the number of offices times 300. Then you add the number of directions there's views times 1,000. And then you get your predicted rent. Does anything there seem off if you're trying to predict rent? Yeah.
I would say views, maybe because it's hard to quantify.
What I meant by this was just like how many directions of the 4 cardinal directions can you get? Oh, yeah, I mean, it's hard to quantify is there a view or not. But let's say, I mean, it's an approximate method. It's not going to be perfect. Yeah. Yeah, exactly. When the distance to BART increases, the rent will probably go down. And so this number should probably be negative. So that should give, so there's an example of how, like, there's some intuitive meaning here. So the higher this number, the more square footage matters for the rent. If it were negative, I mean, that would be equally silly, where you'd be paying less if there's more square footage. But this one, as distance to BART increases, the rent for the office is probably going to go down rather than up. Okay. So here's that slide I showed you, corrected, where this is our weight vector. This is going to be the feature vector, which differs from data point to data point, and so then the output will differ from data point to data point, which is good. And I'll just add, there's a little subtlety here, which is in the example I showed you, there's a constant feature, and you can either have that, or what you can do is you can add a constant here. So I don't know if you guys are probably more familiar, at the very least, with like best fit lines in 2 dimensions, where you have a scatter plot and you're trying to fit a line through, and that's going to be determined by the slope and by the intercept. So this is kind of like the intercept term. But if you have a constant feature, then that would just get baked in. So either you need to make sure one of the features is a constant, or you need to add this extra W0 here. Otherwise, you're forced to predict 0 when the feature vector is 0, and that might not be what you want to do. So you can do either of these. When we're doing the math, we'll just assume that there's a constant feature in the feature vector because it's fewer symbols to push around. But in some libraries, they won't make you do that. They'll just say, yeah, and they'll so they'll basically be solving it like this. Okay, so here's a picture of linear regression with a 2D feature vector. So the picture's in 3 dimensions, but the feature vector is only 2 dimensions. That would be this x1 and x2, and here are all these points. And then the y is the predicted, the y is the observed value for these points, and the y is the predicted value along this plane, which is the predictions at all the different locations. So like in perceptrons, we're taking in data and we're using that to make predictions about new data points. The error is called the residual, so these have high positive residuals because the true value is bigger than the predicted value by the linear regression. These have high, or however you want to say it, high negative or low negative errors compared to the prediction. By the way, I was just searching Google for good pictures for presenting linear regression, and I couldn't find any, so I just went to Claude 3 and said, write me some code to make a diagram for linear regression, and it basically came out with this. So that was cool. Okay, you guys talked last time about vectors. If you have a tuple like this, you can think of it as a point on a coordinate grid, or you can think about it as an arrow that goes from the origin to that point, but then you can kind of forget about the coordinate grid underlying it. Obviously, vectors can be more than 2-dimensional, but they're harder to see. And you talked about the dot product. So the way you compute the dot product is you go through each pair of corresponding indices in the vectors, you multiply them together, and then you add the whole lot. Or you can think about it as the product of the magnitudes of the vectors, how long these vectors are, which you could compute using the Pythagorean theorem if you're given their coordinates, times the cosine of the angle they make. So the closer aligned vectors are, if you're fixing their magnitude, then the closer aligned they are, the larger the dot product. If they're pointing orthogonally or 90 degrees away, then it's 0, and if they're pointing opposite each other, then it's negative. So here's our example from before. In vectors, I haven't actually checked to make sure that these should have a dot product that's positive. Whatever. Here's one vector, that's the weight vector. Here's the feature vector for a given point. And so these would have a positive dot product. Here's a feature vector for another point for a different office. And the dot product here would be negative. So the dot product, W dot F, is the prediction, the predicted rent in this case, given those stats about the office. And so this is basically the same question. How far does the vector F go in the W direction? If it's going off to the side, then it goes 0 far, and it would output 0. If it's going away, then it's negative far in the W direction, and it would give a negative outcome, which is not really plausible for this example. And here's a drawing of W in this picture. So you can kind of see that it's going up when we go in the x2 direction, and it's also going up in the when you go in the x1 direction, but it's going more up in the x2 direction than it is in it's just going a little bit up in the x1 direction. It's a little hard to see when you flatten it into this image, but there's this drawing of W. And note that this lives in the plane of the feature dimensions. So it's not, it doesn't have, Y doesn't come into this. This is just, W has 2 dimensions, just like X has 2 dimensions. Okay, so I've told you that we'll have data points X and we'll have targets Y. And so, we'll have this cloud of points that we're trying to come up with a best fit to. But I haven't said yet how we get W. In the last class, there was an algorithm for getting W where you went through the points and you saw if they were misclassified, then you changed it to make the decision boundary kind of move out of the way to get that point closer to the right side. And so now I have to tell you about an algorithm for coming up with W. So the rows here in this X matrix are data points. So this would be for a particular office. This would be the square footage, maybe. This would be how far it is from BART. This would be whatever the other features I showed you. And then a column in this matrix is different values for the same feature. So this is the square footage for all these different offices. And here is the market rents for all these different offices that we've observed. And we use this information to try to predict what the market rent would be for other offices where we haven't seen the market rent yet. So X and Y are known, W is unknown. We have to compute what it should be. Any questions here? Okay. I just threw a matrix at you, and it doesn't. The rows and the columns are sometimes it's. I don't like staring at matrices, so sorry, but it makes it easier to do computations when you put the numbers in this kind of array. So, just as a reminder, a row is a data point in this matrix. So, to find the weights, let's think through some operations that we can do. So first, what does the matrix product XW look like? Anyone who's comfortable with linear algebra want to give this a go? It's fine. If not, I'll just tell you. Yeah.
You just take the columns and linearly combine them.
Yes, you can take. Yes, that is a true statement. The way you do matrix multiplication, at least the shape of the output you'll get, the number of rows will be equal to the number of rows of the matrix on the left, and the number of columns will be equal to the number of columns on the right. So this will have capital N rows and 1 column. So it'll be a vector like W and Y. And yes, that's the way that you compute it. So for example, what is the entry in the first row and the first and only column of this new vector XW? So the way we do that, if we want to get the entry in the ith row and jth column, we take the ith row of the matrix on the left, the jth column of the matrix on the right, we take the dot product of those, so we go through all the entries, multiply them together, add up the whole thing, and that's our answer. So for this first row and first column, we take the first row, dot product with the first and only column of W, so that's going to be, I can't point at my screen, that'll be 1 times W0 plus x11 times W1. There you go, that's what it is. And note, this is what we were looking at before. Here it is. It's the dot product of W times this feature vector, or you can think of it as the sum going through each index of the weight for that feature times that particular feature. Yeah?
Is XW related to Y at all? Is it like its own?
Well, we want XW to look like Y. So this XW is our predicted Y, and Y is our real Y. So this is why I went through this exercise. I mean, I knew this was the right thing to look at, this product XW. But it turns out that's what we want from W. So remember, w hasn't been set yet. We have to try and figure out what value w should be. And the criteria by which we set w is that we want this to be true. We want this to be close to y1. If we replace all these x's with 2's in the superscript, we want that to be close to y2. So this is our objective, and the objective is going to point us toward the solution. Okay. So the premise of linear regression, then, is that for any weight vector w that we're thinking about using for prediction, this is how bad it is. Its badness is the magnitude of this vector squared. So xw is a vector we want to look similar to the vector y, so we subtract them. That gives us a new vector. If these vectors were close together, then the difference vector would be small in magnitude. We square it because it then becomes easier to optimize, but obviously minimizing the badness of this is equivalent to minimizing the badness of the square root of that. So this notation with the absolute value bars just means the length of the vector, and according to the Pythagorean theorem, the length of the vector squared is equal to the sum of the squares of all the orthogonal components of the vector. So you can write it like this, or you can write it as the vector dot product with itself. So then, the badness of a weight vector w is the sum over all the data points of the feature vector for that data point times the weight vector minus the value that we wanted it to have. So this is like the error, this is the square of the error, this is the sum of the squares of the errors of the prediction on all the data points we've actually seen. And what people actually do is they divide by 2 to make some other math look nicer. Doesn't really matter. And they call this badness the loss function. And that might be a term that you've heard before applied to neural nets, if you've heard anything about them. Okay, here is the attendance code. And you can stare at that for a little while, and I will take any questions on it also. Any more questions on this? What we're trying to accomplish when we set the weight vector? Yeah. H, yeah, that's just the symbol we used for this dot product. So did I write that wrong in here? Yeah, this shouldn't be. Well, while you're looking at this anyway, let me correct this slide. Because that is, that's like already including the W. I can either delete this W or I can turn this into an F. So that's just the feature vector dot product. Come on. There we go. So the this whole thing together can also be written H sub W of xi. Okay. All right. So that's our objective, but how do we solve it? We're getting closer. So we want to solve for W. We want to find the W that minimizes this loss function. And I'm going to show you some linear algebra in case any of you are interested in that. If you find this, we haven't set you up to understand this, so if you understand it anyway, good for you. This is the sort of algebra you do to try and solve it. You'd get into much more of this in 189, but I'll just show you the kind of gist. So if we're going to try and find the argmin of this loss function, then the gradient there, which is basically a multidimensional derivative, will be 0, because the best or worst spot is going to be flat. So we are going to want to calculate the gradient of this, set it equal to 0. Why did we make this substitution here? One of the identities I showed you before is that the magnitude squared is equal to the vector dot product with itself. So here's this vector. Take the transpose so it's horizontal, and then the matrix product gets you a single constant. So that's another way of writing the dot product. So we set that equal to 0. We expand this out. This might look familiar if you're just doing, it's similar to the distributive law in normal algebra. These two terms end up being the same, even though they look a little different, so you simplify it like that. And then you take the gradient, and it turns out you could just do that for these sorts of expressions. Taking gradients with matrices involves kind of intimidated me at first, but you can do it. And actually, if you ever actually need to do this stuff, what I do and what a lot of people do is they just go to this website. This guy came up with all the stuff you're ever going to need, and it's great. So there you go. If you want to understand this more, go to that link. But what this means is you can get an answer out. And I'm sorry I can't really fully justify it for you in the scope of this class, but this is the lovely thing about linear algebra. You can move things around and come up with closed form solutions. So this W hat is the W which minimizes this expression. Here we're taking a matrix inverse. You can actually do a pseudo inverse if you're familiar with that term. So you have a matrix here, a vector here. You multiply it all together, you get a vector, and that's your answer. And people have known about this identity for hundreds of years. Any questions that are not just like, what? Yeah.
So the deriving is not really, it's not out of scope, but the one in the box is.
Let me get back to you about whether you actually need to know, whether you actually need to remember this. But certainly you don't have to derive it. You have a cheat sheet, so you can always just write it down. Okay, so that's linear regression. And the example I showed you was like predicting the rent for office space or whatever. But any time that you're trying to predict a number rather than classifying it yes or no, regression is the sort of thing that you'd use. You could use different ways of trying to predict the value, but that's the problem for which linear regression is one solution. So now we're going back to the problem of classification and improving the perceptron. So some problems with the perceptron that Cam told you about last time. One, if the data isn't separable, then constantly trying to change the boundary when you misclassify a point is going to mean you're constantly changing the boundary, like forever. You're never going to settle on a boundary that's stable. And they call this thrashing, which I think is a good word choice. And one thing you might do is kind of average them over time, but it's still a bit unstable. Another problem is that you might find something that is barely separating your classes. So if you got to this one on the side, it never misclassifies, and so you're never going to change it. But clearly, if you saw a new point there, I mean, imagine these lines were gone and there was a new point right where the cursor was. Would you really want to predict that's red? No, probably not. You might not be sure, but if you had to guess, you'd probably say it's blue. And there's this overtraining issue, which is a problem, but it's not. But it's also can be a bit of a problem in what I'm about to tell you. So maybe it's a little unfair to use this to set up logistic regression. Okay, so here's a setting where the classes that we're trying to understand are not separable. So even the best linear boundary is going to make at least one mistake. And so when we make this boundary and we're asked, well, when the classifier is asked, what class would you expect a point here to have, it'll get it wrong, and it'll just, it won't hedge at all. It'll say, yeah, that's going to be a blue point, and then it'll be wrong, and it'll be like, well, sorry. If something has a chance of being wrong, we'd like to kind of know what chance it has of being wrong. So it would be much better for it to give a probabilistic estimate of what the class is going to be. So here it really shouldn't just say like, yes, it's going to be blue, or yes, it's going to be red. It should say, well, you can't really tell from the data, maybe 50-50. And here a more appropriate thing to say would be that it's 70% likely to be blue, 30% likely to be red, vice versa over on that side. Here you'd say 90% likely to be blue, 1% likely to be red. 10% likely to be red, and likewise over there. And as we've seen before, when we were talking about decision making under uncertainty, the value of information, all that stuff, often what we want to know, or maximizing expected utility, is probabilistic estimates of what things are going to be. So perceptrons give deterministic decisions. So let's say we have Z, which is the dot product of the weight vector times the feature vector, the weight vector and the feature vector. And let's say that, here it's -10 is definitely class 0. Here it's -5, definitely class 0. Here it's -0.001, yeah, definitely class 0. Here it's positive 0.001, definitely class 1. Well, that's a little crazy. I mean, there's like a tiny difference, and all of a sudden we've gone from being sure it's this class to sure it's this other class. So this is the result of the rule for perceptrons. If Z is positive, you say, yep, definitely one class. If it's negative, definitely the other class. Sorry, that's a typo. That should be -1. And so you have this step function basically in terms of the credence that it's outputting as a function of Z, which the perceptron is giving you. And what we'd probably want is something a little more smooth. So if this h of Z is the probability that the class is the positive class, then instead of looking like this, it would probably be better to have something that's looking like this, where it's changing smoothly. You never have a situation where a tiny change in Z suddenly changes your beliefs wildly about what you're going to see. Questions about this? Okay. So, kind of redoing that a bit. We have perceptron scoring, same as before. But now we say if Z is very positive, then the probability of the positive class should approach 1. And if Z is very negative, then the probability of the negative class, another typo, that should be -1. Oh no, sorry, here it's correct. Then the probability of the positive class should approach 0. The probability of the negative class should approach 1. Because we're doing binary classification here. We'll get to multi-class later. So what we use for that kind of function that I was sketching out in red before is the sigmoid function. And it looks like this. It's 1 plus 1 over e to the negative z. And I'll explain to you, I'll give you some justification for why that's a reasonable function to use. But you can verify that it has this property. As z gets very large, this approaches 1 because that approaches 0. As z gets very negative, then this blows up to something huge, and so then the quotient goes to 0. So instead of just outputting one class or another, absolutely, definitely, based on whether z is positive or negative, what we'll do instead is have z be the output of the perceptron, same as before, and then phi of z be the probability that the class is 1 according to the classifier. And this is going to be our logistic regressor. So here's an example. So we have some w, some constant, some weight vector, basically, that we have to learn. And then wx is the dot product of w and x. So that's our z. We plug it in to this sigmoid function, and we get our answer. So suppose that w is this vector and x is that vector. What label will be selected if we classify deterministically? So this is in the deterministic perceptron setting. Well, we take the dot product, so it's -3 times 1, that's -3, plus 4 times 2, that's 8, plus 2 times 0, that's 0. So we add them together, we get 5. 5 is positive, so we say it's the positive class. Maybe that was spam in this case, and the negative class was ham. 5 is positive, classifier guesses the positive label, that's it. Okay, now let's switch back to the logistic regression setting where we're giving probabilities rather than just saying yes or no. So what we do here, we do the same dot product, w times x, but now we say the probability of a positive label is 1 over 1 plus e to the negative that. So that's 5, and this computes to just over 99%. So it's very confident, but not 100% confident, which is kind of the implication of the perceptron. And so that leaves less than a 1% chance of a negative label. So there's an example of that. Here's a picture of an example in one dimension. So we're classifying either red or blue. So red is the positive example. So, and you can see that as x increases, you're seeing more reds. As x decreases, you're seeing more blues. So these ones are kind of definitely red. These are definitely blue. These ones you're not sure. So you can still call it a decision boundary, but it's not a sharp decision boundary. This is just the setting where your probability for one class or another is 50%. And so when you're on one side, you're not suddenly saying, oh, it's definitely this. You're saying, okay, well, maybe it's 51% chance that it's red here, 51% chance that it's blue over there. And so the probability that it's red at a given spot goes smoothly from 0 on this end up to 1 on this end. So here it's almost 0, there it's almost 1. And w is some, well, here it's a weight constant because it's a vector with one entry, because it's a one-dimensional problem. So, you know, I just kind of pulled this function out of thin air, the sigmoid function, so I'll give you a bit of intuition for where it came from. I haven't actually looked into the history to say that, like, it actually comes from thinking like this, but it must. Okay, so suppose we have two hypotheses. We have a coin, and it might have a bias towards heads, or it might have a bias towards tails. So hypothesis A says, this is a coin that comes up heads 2/3 of the time. Hypothesis B says, this is a coin that comes up tails 2/3 of the time. We don't know which is which. We don't know which it is, but we know it's one of these. Kind of a contrived problem, but we'll work through what we can believe about it in that setting. Every time we see a heads, this is like a bit or a factor of 2 of evidence in favor of hypothesis A, because hypothesis A was basically was putting twice as much probability on what we actually saw. Hypothesis A said, yeah, I kind of thought we'd see a heads. I said that was 2 in 3 chance. And hypothesis B was saying, oh, I was kind of expecting it to be tails. I mean, it could have been heads, but it wasn't really what I was expecting. So hypothesis A is putting 2 times more probability mass on the heads that we actually saw. And every time we see tails, that ends up being a bit of evidence for hypothesis B. Our credence that B is correct should kind of go up by a factor of 2. Not quite, but if you think about it in Forget that sentence. Okay, if we have n more heads than tails, then hypothesis A is basically 2 to the n times more likely than B. It's like for every one way for B to be true, there's 2 to the n ways for hypothesis A to be true. So that means that the probability we'd assign to A is 2 to the n over 1 plus 2 to the n. If we divide the top and the bottom by 2 to the n, then we get something like this that looks a lot like a sigmoid function, but we like e better than 2, so we say e instead of 2. And that's our sigmoid function. There was like that kind of expression I just saw. Obviously, this is just like a very particular problem. If you had different hypotheses, the way the evidence would evolve would be different. But this at least should tell you that this functional form has something to do with collecting independent evidence over time and putting that into a probability. So as you get bits of evidence that were collected independently, and you put them all together to see what you should learn from that, what you'll end up with is something that is kind of a sigmoid function of the amount of evidence you're getting. So this example should at least say that, okay, something like this function seems like it could be reasonable. Yeah? Because you take the derivative and you don't have an annoying log 2 in the front. If this were e times that instead of 2 times that, we get an e straight out. It's just the numbers aren't as nice. So it's not like, there's nothing fundamental about this problem. It's just a problem where bits of evidence you get are independent from each other. And when bits of evidence are independent from each other, then you can sum up all the evidence and put it through a sigmoid function and get probabilities. And it'll end up working out well. But yeah, mathematicians just like having logs base e rather than base 2 because when you do math, you don't have as many annoying constants hanging around. In that example before, you could replace the e with a 2 and everything would work fine. Okay. So we're still at the question of how, for linear regression, I told you how to find the W vector. For logistic regression, which is what we're talking about now, I haven't yet told you. How do we find the W? So if you think back to maximum likelihood estimation, which we've talked about before, in the context of Bayes nets at least, maybe in other settings too, we choose the value of W that maximizes the probability of the observed data. So we have some observed data. We know, we've seen when x is this, that's a positive instance of the class. When x is that, that's a negative instance of the class. And so if we're coming up with a hypothesis, we want it to retrodict the data. We want it to predict, we want it to assign high probability to what we actually saw. So the likelihood of the training data given this weight vector W takes the following form. It's the product over all the individual data points of the probability of that training data point given the weight vector W. So this weight vector W is basically telling us what probability distribution we're thinking about. So when I say the probability of a training data point, that's basically the probability that this point has this label, given the points and labels that we've seen before. So you can also write that like this: the probability of yi given xi and w. And it's nicer to take sums instead of products, so we think about maximizing the log likelihood instead of the likelihood, and then it's the sum of the log of these probabilities. And I'll break it down a little bit more, and then we'll get to an example. So in this setting with our sigmoid function, what does this look like? So what does this look like? So the probability that point xi has a positive label, the probability that yi equals +1, given that x, takes this form. That's the sigmoid function. So we take the dot product of the w and the x, we take its negative, we exponentiate it, add 1, take the reciprocal, and that's our probability that our model is assigning to y for that data point being +1. The probability, according to W, that the label takes the value -1 is just 1 minus that, because probabilities have to sum to 1. This is the probability that it takes the positive value. This is the probability that it takes the negative value. So we plug this in and it looks a little messy. So let's say, let's see, the example's coming in a bit. Okay, so we're trying to maximize this log likelihood function of the weight vector. So that's the maximum over possible weight vectors of this formula, where these take these values. So it takes a different value depending on whether yi is a positive example or a negative example. That's logistic regression. Let's see an example of it. Yeah, you can say the loss is the negative of it, but we'll get back to that. Here's our example. So we have two-dimensional feature vectors. There's one dimension, there's another. Here are two positive examples, and here's a negative example. So what function are we trying to maximize for this data? First, I'll tell you what the data is. We have a data point 2, 1, and the class is positive. We have a data point 0, -2, and the class is positive. We have a data point -1, -1, and the class is negative. And then what we're trying to maximize is this. Okay, that's what I showed you before, but what does that mean? Here it is. It's messy. Sorry. Here is our first data point. So we've taken 2, 1, and we've taken the dot product with W. So W has two values. It's a dimension 2 vector, so it has W1 and W2. So 2 times W1 plus 1 times W2, there's our dot product. There's the sigmoid function of it, so that's the probability of a positive example. It was a positive example, so that's the probability we're interested in. And then we take the logarithm of that. That's the log probability of this data point according to our model. We do the same thing for this second data point down here. Here the dot product is 0 times W1 plus -2 times W2, so there it is there. And then for this third data point, we do this dot product, so it's -1, -1, so here it is, the dot product with the W vector. And then we do 1 minus that. Why 1 minus that? Because the probability of a negative example is 1 minus the probability of a positive example. And it was, in fact, a negative example, so we're interested in whether our model assigned high probability to the negative possibility. In other words, we're interested in assigning low probability to the positive possibility. So even when you just have 3 data points, and they're 2 dimensions each, this equation can get a little unwieldy, which is why we presented it in the more symbolic, but maybe a lot to wrap your head around way before. And then we take the argmax over W. So this is an argmax over both the value of W1 and the value of W2. Those are our free parameters. We move them around to try to make this expression as big as possible, which doesn't look like fun, if you ask me. But that's what we're trying to accomplish, and we'll use a computer to do it so that we don't have to do it ourselves. Any questions about this example, where any piece of this equation came from? Yeah? That was from these data points. So this is our x. This is one of our x's. And so we do 2. So we're doing this vector times the dot product. Well, this vector dot producted with the vector w. The vector w is w1 comma w2. So that's 2 times w1 plus 1 times w2 is the dot product, which is written there. Yep. It isn't. It ends up being okay. You can't solve it. I don't think you can solve it analytically like you could with linear regression, where you just like move things around and the answer pops out. But there ends up being a pretty good algorithm, which I'll tell you about soon, which makes it pretty quick to solve this. One of the reasons it ends up being pretty quick is, and lucky we're in 2 dimensions so you can visualize it, So our two dimensions are W1 and W2, right? This function that we're trying to maximize ends up being kind of, it only has one peak. It ends up being concave. And so if you just kind of keep moving to the top, you'll get there. When you're dealing with lost surfaces that are like that, it can be hard to do it, but this ends up being pretty efficient. But yeah, it's not obviously efficient, that's for sure. Okay. So let's go back to this setting where we're classifying between positive and negative examples, and it's separable. There's a way to draw a line between all the points that are in one class and all the points that are in another class. When we were doing the perceptron, these would be equally stable solutions. If your perceptron ever ended up with a boundary like this, it would never move. Same for over here. But intuitively, we prefer this one because, look, if there's a point right there, we're not going to want to classify that as blue. Okay. In the logistic regression setting, these are not equally good outcomes. And here's why. So in the logistic regression setting, if you're assigning 50-50 here, then you're saying, it's like 70-30 here, 30-70 there. Whereas here, you're doing it like this. And we'd rather our model assigned 75% chance to red here, because it would be right, instead of 52% chance to red there. I mean, they're both getting it right, but this one was more confidently right. And so this puts a higher probability on our data set. When we're maximizing the likelihood to find our W vector, the W vector that gives us this picture gets a higher score than the W vector that gives us this picture, because it's putting more probability mass on the truth. Likewise over here, this model is saying, okay, it's just barely more likely to be blue. This one is saying, no, we can be pretty sure it's blue. This is pretty far from our decision boundary. Okay. Multi-class logistic regression. Maybe I'll pause just to make sure. And it's okay if you have questions about prior slides. Anything you want to ask about this. Anything you want me to go over again. I think we're doing okay on time. Yeah. Nope, that's a different algorithm. The support vector machines they're related. They also give you deterministic answers instead of probabilistic answers, although you can modify them to give probabilistic answers. What a support vector machine will do that a perceptron will not is it will prefer this one on the left to that one on the right. What a support vector machine is trying to do is maximize the margin between it's like, so you move copies of your line out from your line, and you want it to be the case that you can go as far as possible without running into your data points. So that's how a support vector machine would prefer this one to that one, but it's still not going to give you a probabilistic answer. Okay, cool. So multi-class logistic regression is going to be kind of analogous to multi-class perceptrons, basically using a similar trick. So with perceptrons, we have a different weight vector for each class. So let's say we have classes 1, 2, and 3. And then we take our feature vector and we multiply it by each of those different weight vectors. And then whichever gives the highest dot product is our prediction. So if we have some vector maybe over here, then we take the dot product with this, we take the dot product with this, we take the dot product with that, we compare those three numbers, we find that the dot product with this will be the biggest, so we say this is one of the yellow classes. And this has the same problem. Just as we go past a decision boundary, we go from completely sure that it's going to be this class to completely sure that it's going to be that class. It's not very robust. It's not going to tell us how confident we should be. So let's turn these scores into probabilities. Here are our scores. Here's W1 times our feature vector. Here's W2 times our feature vector. Here's W3 times our feature vector. And when I say times, I mean a dot product. We're multiplying vectors. And then we turn them into probabilities like this. We exponentiate them, and we say that the probability is going to be proportional to that exponent. So we take e to the z1 divided by the sum of all these exponentials. Same for these. You can see that these are going to sum to 1. And this is this coming? There's some like... Is there a ghost in here? I promise I'm not just going like... That is disconcerting. All right. Okay, they're going to sum to 1. That's good. They're going to be positive. That's great. These are perfectly good probabilities. You can see they kind of look like sigmoid functions. It ends up, yeah, it is basically just a generalization of the sigmoid function. So these are our original activations, and these are they're called softmax activations. If you've programmed a neural network in PyTorch, maybe you've called the softmax function. I really don't like that. Okay. So there's what I just showed you. Let's look at an example. So here is our feature vector for one data point. Here are our 3 different weight vectors. They'd all have to be trained separately. And let's see what probability assignment we're going to give to this vector. So if we classify it deterministically, let's first review what we do in that setting. Okay. Then we take these 3 dot products. So the dot product of these 2 vectors, let's see, that's -3 plus 8 plus 0, so that's 5. Taking the dot product of these 2, that's 2 plus 4 plus 0, so that's 6. 0 plus -2 plus 0 is -2. Anyone? Did I lose anyone? Okay. I was just doing the... going through each index, taking the product of the 2 terms, and then adding them together. So, which of these numbers is the biggest? 6 is the biggest. So it's class 2. That's the output of the classifier. No hesitation. Is there... God, Darth Vader's watching. Does this one work? No fixing that. Okay, so if we classify the labels probabilistically instead of deterministically, what do? We exponentiate all these. We take e to the 5th, e to the 6th, and e to the -2. And then the probability of class 1 is e to the 5th divided by that. Probability of class 2 is e to the 6th divided by that. Same for probability of class 3. We get these probabilities. And you can see, yeah, the dot product is higher with this weight vector 2, but it's not way higher than weight vector 1. These are pretty close. And so we shouldn't be totally sure it's class 2. Maybe it's class 1. And so that's a much more hedged answer. Okay, so how do we actually come up with the best W? We have to redo this since it's a slightly new problem, multi-class instead of binary class. So here's our maximum likelihood estimation. We're maximizing the likelihood of the training data. That's the product of the probabilities on all the individual data points because we're treating them independently. That's the probability that a point here gets this label. That's the probability of this yi given the xi and the w. Then we take the logarithm, so we're dealing with a sum of log probabilities. In addition to it being nicer to work with sums, it's also nicer to work with log probabilities because you don't get underflow issues. If you're dealing with probabilities that are like 10 to the negative 20, and then you're trying to subtract other probabilities that are extremely small, the floating point arithmetic doesn't work as well. And so if you take the logarithm, then you have lots of bits of precision, and you can do the operations more accurately on a finite computer. Okay. So we do maximum likelihood estimation again. So here's our log likelihood function of given our weight vector. So we have the sum of the log probabilities all given the weights. And now this bit in here takes a slightly different form. The probability that we get a given label at a given data point, well, that depends on the weight vector associated with that label. So let's say we have 3 classes. yi could take a value of 1, 2, or 3. Then we have our w1, or we have our w2, or our w3. So here we're summing over all the different possible labels that we could have, summing over all the different classes. And we use our weight vector associated with each of those classes. So this is multi-class logistic regression. All our different data, we'll go through all our different data points. That's this sum here. And we'll calculate its feature vector, or just read the feature vector, really. We're not doing calculation of feature vector here. And then we'll pick the right weight vector for that point. So, if we have n data points, we're going to be doing this whole thing n different times. We're not going to have n different weight vectors. We're going to have 3 different weight vectors or 5 different weight vectors, however many classes we have. And we'll pick the right one depending on the class that we actually saw. And that's how we'll compute this, and then we'll divide by the sum over all the different possible classes. So here's an example, multi-class logistic regression. So we have 3 classes, red, green, and blue. We've seen that a point there has the classification red, a point there has the classification green, there for blue. Same as before. So the data point at 2, 1 is now red, 0, negative 2 is now green, negative 1, negative 1 is now blue. And now we're maximizing over 3 weight vectors, really. So last time W had, there were 2 parameters buried in that symbol. And now there are 6 parameters buried in that symbol. We need the x-coordinate of W1, the y-coordinate of W1, x-coordinate of W2, y-coordinate of W2, same for W3. But we're trying to maximize this function. So here it is. Sorry, your code will deal with this. You don't have to write all this out. Rather than putting even more subscripts and superscripts on, we've just labeled these W2s as different. So this W1 is different from that W1. This is red W1. This is blue W1. So this is 6 different values: red W1, red W2, blue W1, blue W2, there for green also. And so we're trying to maximize, we can set all those 6 values however we like to maximize this expression. So here is the dot product of this data point, 2, 1, with the red weight vector. This is the dot product of this data point with the blue weight vector. This, let's go here. This is the dot product of the blue data point with the blue weight vector. So this is just an example of the formula I showed you before. This is basically the probability that the model assigned to the correct answer for this data point, the probability that the model assigned to the correct answer for this data point, and that one for that one. Take the logarithms, add them all together. That's the log probability of the total. And then we maximize this. And you're not going to want to do it by hand. You can't solve it analytically. So we'll need some algorithm that maximizes the function. So we're getting there. I mean, I still haven't told you about how we get the weight vector in binary classification for logistic regression. I haven't told you how to get the weight vectors, plural, for multi-class logistic regression, but I've at least told you how to recognize which weight vectors are better than others. So this is the function we're trying to maximize, and then we'll get to programs that can help us maximize those functions. Yeah?
How do you get one of the components from the denominator again?
You take the data point that you're thinking about. So here we're thinking about this data point up here. And we take the dot products with each of the weight vectors. Sorry, they're not shown on here. But the red weight vector is here, the blue weight vector is here, and the green weight vector is here. So here you can see index 1 always gets multiplied by 2, and index 2 always gets multiplied by 1. And that's because we're taking the dot product for this data point. So we're on top, we're just taking the dot product with the vector associated with the class that it actually is. On the bottom, we're taking the dot product associated with all of the different classes in turn. So that's how we get these things in the denominator. I'll show you, I'll go back to the general expression here. More compact, but more symbols involved, kind of. So this is the sum over all the different possible classes. Whoops. The sum over all the different possible classes of the feature vector times the weight vector associated with that class. And here it's just the dot product with the weight vector associated with the class that it actually is. I'll give you a second with that. Yep.
So it takes like the actual class and then divides by everything else.
Yeah. And the reason, and so this is, let's see. And that's because of this. So these z's, remember, are the dot products of the feature vectors with the various different weight vectors. So here are like our different weight vectors. And then z1 would be when you take the dot product of x with w1. z2 would be the dot product of x with w2. And so, and this is just the definition of the probability that the logistic regressor is outputting. And so if we're judging the logistic regressor on how much probability it's assigning to the actual correct answer, then we just have to see, okay, well, what probability is it assigning to the correct answer? Here it is. Here's how it calculates its probabilities, so that's what we're judging it based off of. I don't know if anyone in the audio booth up there has any ideas for the Darth Vader noise. Okay. So there it is abstractly. There it is as an example. And maybe that'll show you why to write it abstractly. So this first term, that's the log probability of a point at this location being red. The log probability of a point at this location being green, yeah, and for blue, yeah.
I'm just kind of confused how the denominators are different.
Different in these three terms, you mean?
Yes.
Okay, so we want to judge. So the truth is this point's red, so we want to judge how well the logistic regression algorithm with that weight vector, with those weight vectors did at predicting it would be red. So how, if you run this point into a logistic regression algorithm, how do you get its predictions for what color it would be? The way you get its predictions is using this formula here. Whoops, where'd it go? Using this formula here. So you take your 3 different weight vectors, and you take the dot product with the location where you actually are. If you want to know, I mean, for it to make its prediction about what color it's going to be at this location, it's going to just look at the weight vectors, and it's going to look at the vector where you actually are. And so that's why you're always taking the dot product with the same x vector. Because if you're going to make a prediction about what class you'd see at this location, that's the relevant piece of information. And so you see how well does this align with this weight vector versus that weight vector, this versus that weight vector. That's the numerators for your 3 probabilities. And then you normalize them to make them add to 1. And then if you want to see how much probability did it assign to the true class, you don't care how much probability assigned to other classes. You just want to look at one of these 3. Which of these 3? The one that was actually ended up being correct. So if the correct answer was that it was class 3, you care about this number being high. You don't care about these numbers being high or low, except in as much as they need to be low for this to be high. You really just care about how high is this number. And so that is why in the numerator you're only having the relevant color, the color it actually is. But the denominator is still just the normalizing term, which includes everything. Okay. Before we get to actually finding the optimal W's, I'll just show you a bit of what this softmax function looks like when you have different bases. So the question why E versus why something else. You could choose something else. If you choose something else, you'd get something that's kind of steeper or less steep. So if we replace E with e to the 5th, so multiplying by 5 here is basically changing the e to e to the 5th as the base. So this is a bigger base, and you end up with something that's steeper around the decision boundary. If you made the base e to the 100, then it would look a lot like the step function decision boundary. So yeah, that's basically looking just like the maximum. If you had so 2 is a little less than e, so it would be a little less steep. I'm going to skip this. If you're interested in verifying exactly how the sigmoid is as an example of the softmax thing, you can look at this. But I mean, it doesn't look too implausible if you just glance at it, and it's pretty boring. Okay, so next up, and I'll just start to get into this time, and then we'll go into it properly next time when we talk about neural networks as well. Optimization. So how do we solve the maximum of the log likelihood function of the weight vector? And that is optimization. So let's start with a review of derivatives and gradients. What is the derivative of this function? 2x, great. What is the derivative of this function evaluated at x equals 5? 10, great. So we plug in 5 for x. Okay, gradients. Raise your hand if you have seen gradients in a class before. Good, cool. So what's the gradient of this function, x squared y? Recall a gradient is a vector of partial derivatives with respect to each variable. So we calculate the partial derivative with respect to x. That's basically treating y as a constant. And then the partial derivative with respect to y, which is treating x as a constant. So the partial derivative with respect to x here is 2xy, because y is like a constant. And the partial derivative with respect to y here is x squared, because this is just like some constant times y. Any questions about that? Okay. And then we can do the same thing. We can evaluate the gradient at a particular point. And so then we plug in the values like that. and we get, there's our gradient. It's a vector. Derivatives, new and improved, multidimensional. So even though we're just evaluating one function at one point, because it's a function of multiple variables, this gradient will be multi-valued. The general approach we're going to use for optimization is hill climbing. And so if you remember from local search, this is a basic idea. And the idea is we start wherever we start, could be randomly, and then repeatedly we move to the best neighboring state. If no neighbors are better than the current state, then we quit. But there's an issue when we're doing hill climbing for logistic regression or multi-class logistic regression, which is the weight vector is in continuous space. The weight vector is some vector of real numbers. You know, they could be, you know, you could go from 2 to 2.06 or whatever. There's no finite set of neighbors. So we're doing optimization over a continuous space, which means we have infinitely many neighbors, and which means we need a slightly different approach. So the way we do this efficiently is we use gradients. So here's a one-dimensional optimization problem, and actually one thing we could do without gradients, which would be fine in one dimension really, is we just try increasing by h or decreasing by h, see which is better, we go in that direction. Or what we could do is we could evaluate the derivative here, and we can see whether going to the left or to the right brings us up. So if the derivative is positive, then we're going to want to go to the right to get a bigger value. If it's negative, we'd want to go, if we were here, say, then the derivative would be negative, and so we'd know we wanted to go left to get a bigger value. But once you go beyond 2D optimization, there's really the analogs of this first option start to look a lot worse, and the analogs of this second option continue to look equally good. So if we were over on the side here, there's infinitely many different directions we could go in, and we don't want to try them all. We just want to know which way to go, and the gradient tells us exactly which way to go. So gradient ascent works as follows. We perform an update in the uphill direction for each coordinate. So the steeper the slope, that is, the higher the partial derivative, the bigger step we take for that coordinate. So if the partial derivative in the x direction is 8, and the partial derivative in the y direction is 1, then we're going to want to increase both x and y to get a bigger value of our function. But we're going to be most excited about increasing x because the function increases fastest in that direction. So we're going to want to go in a direction that's increasing x and also increasing y, but maybe we're going to lean more toward the x direction. So let's say we have some function g. That's not gradient g, that's just some arbitrary function g that is of 2 values. Let's say they're the 2 coordinates of the weight vector. Then our updates look like this. Whatever w1 was, the way we change it is we add some constant alpha times the partial derivative of our function with respect to that parameter we are interested in updating. And then we do the exact same thing for this other parameter. So this alpha is going to be some small number, and we'll talk more later about how you pick it. But in vector notation, the way this looks is we take the vector w and we add to it alpha times the gradient of this function. Whichever you prefer to think about, just ignore the other one. They're both the 2 ways of saying the same thing. So this is the rule for gradient ascent. And I just wanted to get to this picture. This is what it ends up looking like. So if this is like, I don't know if you've seen a topographical map. These are like this is like a hill that's coming up like this, and gradient ascent kind of goes along this path and gets you to the top. And that's the general way that we will be doing optimization. See you on Tuesday.